Thank you, Mr. Chairman. Good morning, ladies and gentlemen. I am glad to be here at CERN today at the 90th birthday of Turkish Republic. It was established in 1923 with the Lausanne Treaty signed in Switzerland. I am not a physicist, I am a mining engineer, and I will evaluate the thorium from mineral processing point of view. This is not the light. Wrong slides.
This is not the right presentation. Sorry.
Muammer Kaya. No. It was on the list. This one.
This one.
Mm-hmm.
Sorry.
Okay, the title of this presentation is Global and Turkish Perspectives of Thorium Fuel for Nuclear Energy. Thorium occurs naturally. It is identified almost 2 centuries ago. Thorium exists in nature almost entirely as a stable thorium-232 isotopes. Thorium itself cannot sustain a chain reaction. It has a lustrous silvery white metal. Thorium is dense and only slightly radioactive. Thorium is fertile material, accepts neutron and transmute into the fissile thorium-233. Thorium is usually a byproduct of rare earth elements containing monazite and bastnasite minerals. It's plentiful in nature, as told yesterday, and virtually inexhaustible fuels. It's a thermal breeder. It's important to make nuclear weapons. It is not possible to make nuclear weapons and bombs from thorium. Nuclear power without proliferation has obvious political appeal for most of the governments in the world. Thorium has a high heat capacity, does not require costly mining and mineral processing methods, which is less expensive. Thorium is extraordinarily efficient nuclear fuel. It produces more neutrons per collisions, therefore 20 to 40 times more energy is generated, less fuel is consumed, and 47 times less radioactive wastes are produced. Thorium is a fuel completely used up in the reactors, and the wastes to be stored for only a few hundred years, not for a few thousand years. Thorium reactors have zero risk of meltdown, and thorium reactors can use liquid fuels. Thorium is 3 to 4 times more abundant in the nature than uranium, and most importantly, evenly distributed throughout the world. Thorium can be mined with relatively cheap and environment-friendly mining methods from high-grade alluvial deposits. Extraction is relatively simple. Thorium has a better radiation stability and longer fuel cycles. Thorium has a higher energy density and fuel economy. Thorium mixed oxide fuel can be burnt in any reactor that can license to use MOX. And there is a huge spent toxic plutonium that has been piled up from thorium fuel. Thorium fuel can be used to safely incinerate these unwanted stockpiles. Today, uranium is the preferred fuel for commercial reactors. And uranium has been adequate to meet today's supply needs. Uranium reserve is around 5.5 million tons in the world, and yearly production is around 65,000 tons. There are about 19 uranium producers, and the life expectancy of uranium reserves is around 50 to 60 years. Uranium ores are generally not harmful. Reactors require extremely rare uranium-235, and uranium mining, enrichment, and extraction are expensive and complex processes. Uranium fuel leaves large amount of toxic wastes, and depleted fuel can be reprocessed by expensive Purex process. Here we can see the world reserves of thorium by OECD. Reasonable assured reserves of thorium is around 2.2 millions, and the estimated additional reserve is 2.1 millions. Brazil has the highest reserve, and Turkey has the second highest thorium reserve. Here we can see some of the minerals containing thorium. Monazite, thorite, and bastnasite, those are the minerals containing both rare earth elements and thorium. Monazite contains 0 to 20% thorium, while bastnasite contains 0 to 0.3% thorium. Monazite, a phosphate mineral with rare earth oxide content of 70%, and it was found in granites, cyanides, pegmatites, and beach sands. World monazite reserve is estimated to be 12 million tons. This ores includes 3 to 14% of thorium and variable amount of uranium. Monazite deposits are found in beach sands and also component of the Bayan Obo deposit in China, which is the biggest rare earth deposit in the world. World production changes between 5,000 to 6,000 tons per year, and Australia, India, China, Brazil, and Malaysia are the main producers. Thorium from monazite deposits can be mined with relatively cheap and environment-friendly mining methods because it exists in high concentrations and in high grades at the surface or in the beach sands. The ore can be skimmed off by the surface by cheap dredge mining methods. Monazite mining is economical due to the thorium as a byproduct. Uranium mine can be developed in 10 to 15 years, while the thorium mine can be developed 2 to 3 years due to less regulatory scrutiny. Thorium is liberated from monazite by gravitational, magnetic, and electrostatic concentration methods, employing a minimum dangerous chemicals, concentrated acids, whereas uranium is mined by expensive underground mining methods and in-situ leaching methods. Here we can see a typical beach sand treatment process in order to recover the monazite, which contains both rare earths and thorium. Gravity concentration, low intensity and high intensity magnetic separations, and electrostatic separation is used in order to recover the monazite. Bastnasite is a fluorocarbonate mineral with rare earth contents of approximately 70%. Bastnasite is the primary source of light rare earth oxides and accounts for the 80% of the overall amount of rare earth oxide in the earth. In the last 50 years, bastnasite replaced the monazite as the chief source of rare earth elements. Bastnasite has been extracted on a large scale in USA and China today. Expensive underground mining methods are used. Processing mainly depends on fine grinding, gravity, magnetic, and flotation separation processes, calcination, HCl leaching, and solvent extraction steps. Here we can see the uranium and thorium deposits of Turkey. Since we are interested in thorium, here we can see the thorium deposit in Kızılcıören, Sivrisar, Eskişehir, which contains light rare earths and thorium. Eskişehir deposit, Kızılcıören deposit is in between capital Ankara and Eskişehir provinces of Turkey. If you look at this deposit in world respect, this deposit is in the reserve wise in the 15th place in the world, as we see here. With respect to thorium oxide content of some rare earth deposits, Eskişehir deposit is the 3rd place, as we see here in the world. Reserve development studies are continuing at Eskişehir light earth elements and thorium deposits. The first reserve calculations depended on the studies in 1959. In 2011, 2 deep drilling bores were opened. Analysis showed further reserves at deeps. In 2012, 10,000-meter drilling were performed at 39 different locations. Between 2014 and 2017, 116,000-meter drilling will be performed around 300 different locations. This deposit is belong to the ThEC mines of Turkish government's mining company. This deposit contains basnasite complex ore, which is finely disseminated. The reserve is around 30 million tons, and the mineral grade distribution is shown here. There are about 3.14% rare earth elements and 0.21% thorium oxide. And the proved and probable mineral reserve distribution is shown here. Rare earth elements is around 1 million tons, and thorium reserve is around 380,000 tons. ThEC Mine, which is the owner of this deposit, is prepared a feasibility report for the production of yearly 10,000 tons of rare earth oxides and 250 tons per year thorium production. Mining will be performed by ThEC Mines of Turkey. Mineral processing and enrichment will be performed by domestic and/or foreign private expert company with the service procurement tender for 10 years. The products will be marketed by ThEC Mines. Thorium or rare earth elements can be extracted from monazite using hot concentrated sulfuric acid, shown here using the hot concentrated sulfuric acid at 120 and 150 degrees Celsius for several hours treatment. Another flow sheet for thorium concentration, nitric acid or sulfuric acid leaching is performed at very low pH values. Some impurities are precipitated. Either solvent extraction or ion exchange can be used in order to produce thorium nitrate. Then this product is dried in order to remove the water, and thorium nitrate is calcined at 575 degrees Celsius in order to produce thorium oxide. Now, let's have a look at some mineral processing studies carried out in Turkey. In 2002 and 2003, the effects of reosting and thiourea addition on basnasite leaching were studied by these Turkish researchers. Firstly, pre-concentrate was obtained by scrubbing, barite flotation, and fluoride flotation. The pre-concentrate contains about 21% rare earth oxides. After pre-concentration, leaching was performed under these conditions. Leaching was performed at 3 different conditions. Firstly, leaching without reosting, leaching with reosting, and leaching with reosting plus leaching with the addition of thiourea. Without reosting, we have to use very high concentrations of acids, as we saw here. We can dissolve the rare earths, but the consumption of acids are very high. In order to reduce this consumption, reosting was performed at 750 degrees Celsius for 1 hour, and reosting increased the rare earth elements content from 19% to 22%. Reosting leaching after rehousting achieved around 47% rare earth elements dissolution. And secondly, we try to add another extracting agent, thiourea, in order to increase the leaching recovery. As we saw here, when we add 1 molar thiourea and 3 molar sulfuric acid, the rare earth elements extraction goes to the 89%. After leaching, hydroxide and oxalate mixture precipitation from leach solutions were performed, and this product heated up to 900 degrees for 2 hours in order to obtain the rare earth elements recovery of 93.6%. From this study, we can get these results. Rehousting decomposes the fluorocarbonate structure of rare earth elements in the preconcentrate with the formation of fluorocerisite and cerianite as a new phase. This change in composition increases the selective dissolution of lanthanum and neodymium in sulfuric acid solution, causing about 6 times increase in the total rare earth dissolution. Addition of thiourea to the leaching medium increases the dissolution of rare earth elements, especially in the rehousted case. 92.6% mixed rare earth precipitation with sulfuric acid thiourea medium was achieved in this study. Another study was performed by MTA of Turkish government in 2004. Pilot-scale acid leach and solvent extraction tests were performed in order to recover the rare earth elements and thorium from the Eskişehir ore. Samples were taken from 3 different districts. Blended size reduction was performed by jaw crusher, cone crusher, roll crusher in order to obtain -1 millimeter composite samples. Then these samples were rehousted in the rotating furnace at 900 degrees Celsius. Then acid leached using 3 molar HCl. After acid leaching, filtration was performed. The solid cake went to the flotation stage in order to recover fluoride and barite, and the filtrate solution goes to the oxalate precipitation in order to obtain rare earth oxides and thorium oxides. From this flow sheet, they achieved around 98.7% thorium nitrate, 84.2% lanthanum hydroxide, and 84% cerium oxides. Another study was carried out in 2012 in order to determine the effect of particle size and rehousting time on thorium recovery using 3 molar sulfuric acid concentrations and 3 molar HCl concentration. Here we can see the optimum conditions for sulfuric acid, and this is the optimum conditions for HCl. The optimum particle size was 1 millimeter for both cases, and the rehousting time was 1 hour for sulfuric acid and 3 hours for HCl. And the leaching recovery, which is the rare earth elements plus thorium recovery, was around 79% for sulfuric acid and 73% for HCl. From this study, we found that 3 molar sulfuric acid gives better leaching recovery than HCl. Oxidizing rehousting at 900 degrees at 1 hour before atmospheric leaching is necessary. The best particle size was 1 millimeter, and 79% recovery was obtained. I would like to conclude my talk from the Turkey's point of view. Energy is the major concern for developing Turkish society. Today, Turkey today exports more than 70% of its energy as fossil fuels. In the last 50 years, Turks are skeptical, anxious, and indecisive about having nuclear energy. In the last 10 years, we are bringing thorium into Turkish government's attention and national discussion as a safe, new, safe, clean, affordable, carbon-free, alternative, strategic, and domestic nuclear energy fuel. In Turkey, we are trying to find supports for education and R&D on thorium. We are expecting to establish a Thorium Research Institute for thorium mining, enrichment, extraction, fuel fabrication, prototype reactor testing, and nuclear fuel testing. Turkey recently contracted 4 Russian type of nuclear reactors using uranium as a fuel in Akkuyu, and another 4 units will be established in Sinop in the next decade by Japanese Mitsubishi company. We will enforce government to use thorium along with uranium as an alternative fuel in the some of the new reactors. And finally, if Turkey can process its important domestic low-grade bosnasite ore deposit in Eskişehir, Turkey, it can supply its own thorium fuel for more than 100 years and become self-sufficient in energy sources. Thank you.